In October of 2021, the world basically just stopped.
Oh, yeah. I remember that day perfectly.
Right. For about 6 hours, Facebook, Instagram, WhatsApp, and Messenger completely vanished from the internet. Just gone.
It was wild. You had people panic buying, rumors flying around about some massive, sophisticated cyber attack.
Yeah, like some nation-state attack or cinematic heist happening in a server farm somewhere.
Exactly. But the reality, I mean, it wasn't a hack. It wasn't a bomb. It was a failure in this deeply hidden, incredibly mundane piece of digital infrastructure.
It's basically the equivalent of the internet losing its phone book.
Yeah. It was a fascinating day to be a network engineer, just watching the fallout. It really shattered the illusion for a lot of people.
Because we treat the internet like this magical, ethereal cloud, you know?
We really do.
Yeah.
You hit enter on your keyboard, and a split second later, a high-definition video is just streaming to your phone.
But that magic is an illusion.
A total illusion. It is a highly brittle, intensely physical, and ruthlessly orchestrated system.
Full of invisible services, handshakes, and these really strict protocols.
Right, and that invisible infrastructure is exactly what we are tearing into today.
Welcome to the deep dive. We've got a really fascinating mission ahead of us today.
We really do.
We are taking a comprehensive guide to modern network services, specifically pulling from foundational materials that IT professionals use to train, like the CompTIA A Plus Module 7.
Which is packed with information.
Oh, totally packed.
Yep.
And we are going to decode the alphabet soup that basically runs your life. We were talking about things like HTTP, SMTP, SNMP, DNS.
What's those acronyms?
Right. We want to map out exactly how the digital world operates around you, behind the glass of your screen.
Which is vital knowledge, by the way. Whether you are actively studying for an IT certification or managing a team or just, well, someone who relies on a smartphone every day.
Which is literally all of us.
Exactly. Understanding these underlying protocols changes the way you interact with technology. You stop seeing it as magic and start seeing it as a machine.
A machine that can actually be understood, manipulated, and protected.
Exactly.
But I want to make a promise to you, the listener, right up front here. We are not just going to read a list of acronyms and port numbers at you.
No, that is a guaranteed way to induce a coma.
It really is. So to keep us grounded, we are going to use a mental framework for this deep dive. I want you to imagine the modern network and an internet, or even just your company's internal network, as a massive, bustling metropolis.
And a digital city.
A digital city, right. And a city needs infrastructure to survive.
It needs roads, postal services, zoning laws, and, a police force. The network is really no different.
Exactly. In this digital city, every single computer, every humming server in a rack, every smartphone in your pocket, those are the buildings.
The buildings of the city.
Right. And over the course of our deep dive today, we're going to explore how we pave the roads connecting them, how the post office delivers the mail, how the bank vaults protect the really sensitive data.
And how the city management team keeps the entire metropolis from collapsing into absolute chaos.
Because it is a delicate balance, isn't it?
Oh, incredibly delicate. The city is always growing, and the older roads have to support traffic they were, frankly, never designed for.
Okay, let's unpack this. Before we can even start walking around this city, we have a fundamental problem to solve. We need to know how to locate a specific building, and once we get there, how to knock on the right door.
The addresses.
Yeah. Now, most people have at least heard of an IP address, even if they don't know exactly how it works under the hood. It's the unique numerical identifier for a device on a network.
Yes. In the context of our metropolis analogy, the IP address is the literal street address of a building.
Like 123 Main Street.
Exactly. It tells the network routing equipment exactly where on the globe or where in the office building a specific machine is located.
But here's something that always tripped me up when I first started looking at this stuff. The sources are incredibly focused on this concept of ports.
Ah, yes. Port numbers.
Right. If the network already knows the street address of the building, the IP address, why isn't that enough? Why do we need this secondary number at all?
Let's stick with the city analogy for a second.
Yeah.
Imagine a massive, multinational corporate skyscraper.
Okay, picturing a skyscraper.
That building has a single street address, right? Let's say 100 Main Street. But a building of that size doesn't just have one single door and one single purpose.
No, it has a bunch of entrances.
Right. It has a grand glass front lobby for visitors. It has a heavily secured loading dock in the back alley for freight deliveries. It has a subterranean parking garage for employees.
And maybe a small side door for the mail courier.
Exactly. So the building is doing a lot of different things at once. Now imagine a massive 18-wheeler truck arrives at 100 Main Street to deliver, say, 3 tons of server racks.
Okay.
If the driver just looks at the street address and decides to drive the 18-wheeler straight into the glass front lobby,
You have a disaster on your hands.
a total disaster. The street address got the truck to the right building, but it didn't tell the truck how to interface with the building.
The cargo gets rejected or crashes because it tried to enter through the wrong door.
The port number is that specific door.
Okay.
See, a modern server is not just doing one thing. A single machine with one IP address might be hosting a website, running an email server, managing file transfers, and accepting remote administrative commands all at the exact same time.
All from one box.
Right. So when a packet of data arrives at the server's IP address, the server's operating system looks at the port number attached to that data.
It's sorting the traffic.
Exactly. If the data is tagged for port 80, the server says, send this to the web server software. If it's tagged for port 25, it says, route this over to the email software.
That makes so much sense. It's essentially triage at the front door.
Triage is a great word for it.
So let's talk about the most popular wide-open doors in our Digital City web services. The doors that handle the actual browsing of the internet. The source material highlights 2 main protocols here, HTTP and HTTPS.
The foundational protocols of the web.
Right. Now, I know HTTP uses port 80 and HTTPS uses port 443. Other than the physical door they use, what is the mechanical difference between these two?
The difference is basically the difference between a glass house and a concrete vault.
Oh, I like that. Security and encryption.
Exactly. HTTP stands for Hypertext Transfer Protocol. It is the original bedrock protocol for requesting and delivering web pages.
But there's a catch, right?
A huge catch. By default, HTTP operating on port 80 is entirely unencrypted. It transmits data in plain text.
Meaning anyone can read it?
Anyone who sits between your computer and the server can read it, yeah. If you are sitting in a coffee shop using their free Wi-Fi and you visit an HTTP website, your data is just broadcasting through the air as radio waves.
It's floating out there.
Right. Anyone with a $50 antenna and a piece of free software can pluck those radio waves out of the air, reassemble the packets, and read exactly what you were doing.
So if I type a password into an HTTP site,
They see the password, letter for letter.
that is terrifying. It's literally like writing your bank account number on the back of a postcard and dropping it in a public mailbox.
That's a perfect way to visualize it.
The mail carrier, the sorting facility worker, anyone who touches it can just flip it over and read it. There is zero privacy.
Zero. And for a long time, the internet operated mostly on that postcard system.
Because we weren't really doing online banking in 1993, right? We were just sharing academic papers.
Exactly. But as commerce moved online, the architecture obviously had to evolve. Enter HTTPS Hypertext Transfer Protocol Secure.
And that operates on port 443.
Yes.
And the sources say it secures the connection using something called TLS encryption, transport layer security.
TLS is the standard now, yes.
But how does that mechanism actually function? Like, how do 2 computers that have never met before, communicating over an open, hostile coffee shop network, suddenly agree on a secret code?
It's pretty amazing, actually. It relies on a mathematical marvel called asymmetric cryptography.
That sounds intimidating.
It does, but let's break down the mechanics. Standard encryption, symmetric encryption is like a safe with a single key. You lock it with the key, you unlock it with the exact same key.
Makes sense. But the problem is, how do I give you the key over the internet without someone intercepting it?
Right. If I slide the key across the table to you, the guy eavesdropping on the Wi-Fi just makes a copy of the key.
And then he can open the safe, too.
Exactly. Asymmetric cryptography solves this by using a key pair.
Pair of keys.
Yes. The server has 2 keys that are mathematically linked, a public key and a private key.
Okay, so public and private.
The server takes the public key and essentially posts it on a giant billboard. It gives it to anyone and everyone who asks.
Okay, so the eavesdropper gets a copy of the public key, too.
They do. But here is the magic mechanism. The public key can only lock the box. It cannot unlock it.
Wait, really?
Really, if you lock a box with the public key, even the public key itself cannot open it again.
That is wild. So what opens it?
The only thing in the universe that can unlock the box is the private key, which the server never ever shares. It guards the private key with its life.
Hold on, let me make sure I'm grasping this. When my browser connects to an HTTPS website on port 443, the server hands me its public key
Yes, immediately.
and say I want to send my credit card number to buy something. My browser takes my credit card data, puts it in a digital box, and snaps the lock shut using that public key.
You've got it.
And once it's locked, my browser can't even unlock it. The eavesdropper in the coffee shop intercepts the box. He has the public key, but that doesn't help him because the public key only locks things.
Exactly. He just has a locked box of mathematical gibberish.
So the box travels all the way to the server, and the server uses its closely guarded private key to unlock it and process the payment.
You've got it perfectly. That handshake establishes the confidentiality.
That is just brilliant.
It is. But HTTPS does one more critical thing. Authentication.
Oh, right, making sure the server is who it says it is.
Exactly. When the server hands you that public key, it's wrapped in a digital certificate signed by a trusted third-party authority.
Like a digital ID card.
Yes. This certificate proves that the server you are talking to is actually your bank and not some malicious hacker spoofing the bank's website in the coffee shop.
So it verifies the identity of the building, and it secures the cargo going in the door. It's incredible that all of that math is happening in the blink of an eye.
Every single time you load a web page.
Okay, so we understand the doors, port 80 for plain text, port 443 for encrypted traffic. But let's zoom out and trace the entire journey of a web request.
Let's do it.
Let's say I open my laptop and type in a URL, a uniform resource locator. The source material breaks this down into 3 parts, right?
Yes, it does.
First is the protocol, like HTTPS. Second is a fully qualified domain name, or FQDN, like www.example.com. And third is the file path, like about index.html.
That string of text is essentially a complete set of instructions for your browser.
So I hit enter, walk me through the mechanism, because my computer doesn't natively know where example.com lives in our digital city, right?
It has absolutely no idea. Computers do not understand human language. They don't know what an example.com is.
They just know numbers.
Right. They only understand IP addresses, those numerical street coordinates. So before your browser can even attempt to send an HTTP request, it has to translate that human-readable domain name into an IP address.
And this is where the phone book comes in. DNS. The domain name system.
DNS is perhaps the most critical, unsung hero of the entire internet.
I believe.
It operates primarily on port 53, usually using UDP for standard quick queries and sometimes TCP for larger zone transfers.
So what happens when I hit enter?
When you type that URL and hit enter, your computer secretly pauses. It sends a lightning-fast DNS query out into the network, asking a very simple question. What is the IP address for www.example.com?
But the internet is massive.
Yeah.
There are hundreds of millions of websites. Does one single DNS server have every single IP address memorized?
No, and that's the brilliance of the system. DNS is a distributed, hierarchical database. It's basically a chain of command.
How does the chain work?
Your computer usually asks your local router or your internet service provider's DNS server first. If that local server doesn't know the answer, it asks the root servers.
The root servers?
Yes, there are 13 logical root servers that act as the ultimate authority for the internet.
Wait, 13 servers run the whole internet?
Well, 13 logical clusters representing thousands of physical servers globally.
Oh, okay. That makes more sense.
So the root server looks at your request for example.com and says, I don't know the exact IP, but I see it ends in .com. Go ask the top-level domain server that handles all .com addresses.
It's pointing you in the right direction.
Exactly. So your query gets forwarded to the .com server. The .com server says, example.com is managed by this specific company's name server. Go ask them.
And then you finally ask them.
Right. Finally, that final authoritative server replies, the IP address for example.com is 93.184.217.34.
This sounds like it should take 5 minutes to resolve, going back and forth like that.
It typically takes tens of milliseconds.
That is staggering.
It really is. Once your computer gets that IP address back, the DNS phase is over. Now your browser can finally package up the HTTPS request, address it to 93.184 and 217.34, tag it for port 443, and send it out across the internet.
So the server at that IP receives it, does the whole public and private key handshake we talked about, processes the file path I asked for, and starts transmitting the HTML code, the images, the styling data, back to my browser.
Precisely. It is a highly structured, relentless cycle of request and response.
And if I type the path wrong, it hands me back a 404 not found error.
Exactly.
But wait, I'm realizing something. We skipped a crucial step for a new cover to the city.
Oh, what's that?
Before my laptop can even ask the DNS server where a website is, My laptop needs its own IP address. I mean, I can't receive mail if I don't have a mailbox.
That is a very good point.
If I walk into a coffee shop and open my laptop,
Yeah.
how do I get a street address assigned to me?
You're touching on a fundamental bootstrapping problem. How do you communicate on a network to ask for an address when you need an address to communicate on a network in the first place?
That's a total paradox.
It is, and the protocol designed to solve it is called DHCP, the Dynamic Host Configuration Protocol.
Now, the sources listed using UDP, port 67 for the server, and port 68 for the client. Why UDT? Earlier you mentioned UDP is for standard quick queries.
Right, so networking protocols generally fall into two buckets, TCP and UDP. TCP is like a phone call.
Okay, a phone call.
You dial the number, the other person picks up, you say hello, they say hello, and you establish a guaranteed ordered connection before you share data. If a packet drops, TCP resends it. It is reliable but heavy.
And UDP.
UDP is like a megaphone. You stand on a street corner and just shout a message into the void.
It's just shouting at everyone.
Exactly. You don't verify if anyone heard it. You don't check if it arrived in order. It is fast, lightweight, and requires no pre-established connection.
So when my laptop opens in the coffee shop, it doesn't have an IP address yet, so it can't make a reliable TCP phone call. It has to use the UDP megaphone.
Exactly. The laptop broadcasts a message to the entire local network on port 67. It's essentially shouting, "Hello, I am a new device with this specific hardware MSC address, and I need an IP address to function. Can anyone help me?"
And somewhere in the back room of the coffee shop, the router is running a DHCP server. It hears that shout on port 67.
Right. The DHCP process is often remembered by the acronym DORA.
DORA.
Yes. Discover, offer, request, acknowledge. Your laptop shouts the discover packet. The DHCP server hears it, looks at its pool of available IP addresses, and shouts back an offer on port 68. I have IP address 192.168.1.50 available.
Then the laptop requests to accept it.
And the server acknowledges the lease.
That's very neat. DORA.
Yes. And it's not just the IP address it hands over. The DHCP server hands the laptop a whole welcome package.
What else is in the package?
It says, here's your IP address. It expires in 24 hours. Here is the IP address of the router you need to use to get to the internet, the default gateway. And crucially, here is the IP address of the DNS server you should use to look up websites.
It basically hands you the keys to the city.
It really does.
And all of this DORA, the megaphone shouting, the DNS hierarchical lookup, the TLS key exchange happens before the web page even starts to visually load on my screen.
What's fascinating here is that it is the ultimate invisible infrastructure. If either DHCP or DNS fails, the entire internet grinds to a halt from the user's perspective.
Like it's just broken.
Right. The web servers might be running perfectly, but if you can't get an IP address or you can't translate a name into an IP, the city is completely shut down.
Which is exactly what happened during that 2021 Facebook outage we talked about.
Yes. Their DNS routes were accidentally withdrawn. The servers were totally fine, but the global phone book essentially deleted their entry. No one could find them.
Unbelievable. Okay, so our digital city is mapped out. We know how to get an address when we arrive via DHCP. We know how to look up other buildings via DNS. We know how to knock on the doors securely via HTTPS. We know where everything is.
We've got a solid foundation.
But there is another dimension to a functioning city: time.
Time, yes.
Because if the mail arrives before the building is built, or a train departs before the passengers arrive, everything falls apart. How does a decentralized global network agree on when things are happening?
Synchronization is absolutely critical, and honestly, it is something most people just never think about. We rely on time servers and a protocol called NTP, the Network Time Protocol.
The sources show NTP operating on port 123, again using UDP. Now, I have to admit, when I first read about this, I thought, sure, the computer needs to know what time it is, so the little clock in the bottom right corner of my screen is accurate.
That's what everyone thinks.
But obviously, in a network context, it goes way deeper than aesthetics, doesn't it?
It goes to the very core of network security and administration. Accurate time isn't a convenience, it is a strict operational requirement. Let's look at it from an administrative perspective first. System logging.
Right, the paper trail.
Exactly. Every server, every firewall, every router is constantly generating logs. They record every login, every file transfer, every blocked connection, and each of those events is stamped with the exact time it occurred.
Okay, I'm with you.
Now imagine you are a security analyst at a major corporation and you detect a data breach. You have a network of 50 different servers, and you need to piece together the attacker's footprints. You need to know if they breached the firewall first or if they compromised an internal database first.
Cause and effect. You need the timeline.
But what if server A's internal clock is 2 minutes fast, server B's clock is 3 minutes slow, and the firewall is 5 minutes fast?
It's a complete mess. Server A might say a file was stolen at 10.04, and server B might say the user logged in at 10.05. You can't tell what actually happened, because the timestamps are contradicting the laws of physics. The user stole the file before they even logged in.
Exactly. Without perfectly synchronized clocks across the entire enterprise, forensic analysis is impossible. You just cannot establish a sequence of events.
That makes a lot of sense.
But beyond just logging, the source material specifically highlights that authentication itself requires accurate time. It calls out a protocol named Kerberos.
Yeah, I saw that. Kerberos. It sounds like the three-headed dog from Greek mythology guarding the underworld. What does that have to do with network time?
Kerberos is a very widely used network authentication protocol, particularly in Microsoft Windows environments. It is how your computer proves who you are to the network without constantly sending your password over the wire. It uses these encrypted tickets.
Okay.
But Kerberos has a major vulnerability it has to defend against called a replay attack.
What is the mechanism of a replay attack? How does that work?
Let's go back to our coffee shop with the hostile network. Imagine you are logging into your corporate network. Your computer sends a heavily encrypted authentication packet to the server.
So far, so good.
Now, the attacker sitting at the next table intercepts that packet. The encryption is strong, so they can't break it. They have no idea what your password actually is.
So I'm safe, right?
Not necessarily. The attacker doesn't need to read the packet. What if they just save a copy of that encrypted packet, wait 10 minutes, and then send it to the server themselves? They are replaying your legitimate login request.
Oh, wow. So the server receives the packet, decrypts it, sees a perfectly valid authentication request from me, and opens the door. But it's actually the attacker walking through the door.
Yes.
They just used my encrypted packet as a master key.
Precisely. To prevent this, Kerberos relies on time. When your computer generates that encrypted login ticket, it stamps it with the exact current time.
Okay, so it has a timestamp.
The server receives the ticket, decrypts it, and looks at the timestamp. It compares the ticket's time to the server's own internal clock. If the ticket is more than a few minutes old, usually the default tolerance is about 5 minutes, the server rejects it.
The server says, wait a minute, this ticket was generated at 10:00 a.m., and it is now 10:00 a.m. This is stale. You must be an attacker replaying an old message.
And it denies access. Now think about the implication of that mechanism. What happens if you are a perfectly innocent, legitimate employee, but your laptop's internal clock has drifted 10 minutes into the past because the battery died?
My laptop will generate a ticket stamped with 9:50 a.m. The server will see that it's currently 10:00 a.m., think it's a replay attack, and block me. I literally won't be able to log in to do my job just because my clock is wrong.
Authentication completely breaks. The system fails closed. That is why NTP is so vital. It is constantly running in the background, making tiny, continuous adjustments to the system clocks across the network to correct for hardware drift, ensuring everyone is on the exact same timeline.
Okay, that makes NTP's importance incredibly clear. But I have a logistical question. Go for it. How does an NTP server actually guarantee that the time it is giving out is the true time? I mean, it's just a computer. Computers can be wrong. The sources mention an architecture involving things called stratum levels. What are those?
NTP is built on a strict hierarchy to establish authority and accuracy. It organizes timekeepers into these stratum levels. At the absolute top of the pyramid, you have stratum 0.
The prime meridian of time.
Exactly. But here's the catch. Stratum 0 devices are not actually network servers. You cannot connect to a Stratum 0 device over the internet. Stratum 0 represents the physical timekeeping hardware itself.
Like an actual atomic clock in a physics laboratory.
Yes, an atomic clock measuring the vibration of cesium atoms, or a GPS satellite receiver pulling time data directly from orbit. Stratum 0 is the unvarnished, absolute, true time.
Okay, so if I can't connect my laptop to the atomic clock, how do I get the time?
Through the network hierarchy. A Stratum 1 server is a computer that has a direct physical hardwired connection to a Stratum 0 device. It is bolted to the atomic clock. It gets its time straight from the source with practically zero network latency.
And then the sources list Stratum 2, Stratum 3, and so on. So let me try an analogy here. Tell me if they had this right.
Okay, let's hear it.
So Stratum 0 is the actual physical clock on the wall. Stratum 1 is a person standing right next to the clock, staring directly at the face of it. Stratum 2 is a person standing down the hallway who has to shout to Stratum 1 to ask what time it is. And Stratum 3 is someone in the next building over who has to call Stratum 2 on a crackly walkie-talkie.
That is a phenomenal analogy. Every time you add a layer of distance, every time you add a network hop across the internet, you introduce a tiny, unpredictable bit of delay, the walkie-talkie static.
Right.
As you move down the stratum levels, from 1 to 2 to 3, the time becomes slightly less accurate because it took a few milliseconds for the answer to travel across the wire.
So if my computer asks a Stratum 2 server what time it is, and the server says it's exactly 12.000000, by the time that message physically travels through the cables and reaches my laptop, it's actually 12.000.01. My laptop will always be slightly behind.
And that is where the true genius of the NTP protocol comes in. It doesn't just blindly accept the time the server gives it. The protocol actually calculates the network delay.
How does it do that?
It uses a very specific mathematical formula. When your computer sends the request, it timestamps it. Let's call that T1. The server notes the time it received at T2 and the time it sent the reply T3. Finally, your computer notes the exact time it received the reply T4.
Oh, I see. By comparing how long the round trip took and factoring in the server's processing time, the protocol can mathematically deduce exactly how many milliseconds the packet spent traveling through the fiber optic cables.
Yes, it calculates the transit delay and artificially advances the clock to compensate. It says, the server said it was 12.000000, but I know this message took 40 milliseconds to get here, so I will set my clock to 12.0000 and 40 milliseconds.
That is remarkably precise.
It really is. For the vast majority of enterprise networking needs, syncing to a Stratum 3 or Stratum 4 server using NTP provides more than enough accuracy to keep logs aligned and Kerberos authentications functioning perfectly.
Incredible. Okay, so our digital city is mapped, the buildings have addresses, the doors are labeled, and every single digital clock in the metropolis is ticking in perfect millisecond accurate unison.
We are ready for business.
Let's actually start moving things around. Let's head over to the digital post office to talk about email services.
Email is a fascinating case study in network architecture, honestly, because it highlights how a seamless user experience is actually a complex relay race under the hood.
Right, because to the average user, email is just one single thing. You click an app, you type a message, you hit send, and it arrives.
But the reality is that email is not a single service. It is a fragmented journey handled by completely different protocols at different stages.
Let's break that journey down.
When you click send, the journey starts with outbound delivery. And the workhorse for outbound email is SMTP, the Simple Mail Transfer Protocol.
The outgoing mail truck.
Right. SMTP has two main jobs. First, it is responsible for taking the email from your personal device, your phone, your laptop, using Outlook or Apple Mail, and handing it off to your email provider's server.
Like handing the letter to the local post office.
Exactly. Second, it is responsible for the massive internet-wide transfer of that email between different servers. When a Gmail server needs to hand a message over to a Microsoft Exchange server, they speak to each other using SMTP.
Now, looking at the sources, they list two specific ports for SMTP. Port 25 and port 587. Why do we need two different doors for the exact same protocol?
This requires a bit of historical context regarding how the internet evolved. Port 25 is the original foundational port for SMTP.
The classic door.
Right. It was designed decades ago when the internet was a small, high-trust environment of universities and government labs. Security was not a priority.
Just getting the mail delivered was the goal.
Right. So port 25 was wide open. But as the internet commercialized, a massive problem emerged. Spam.
Oh, early 2000s spam was the worst.
It was terrible. Malicious actors realized they could write a virus that infects a regular person's home computer and quietly turn that computer into a rogue SMTP server, blasting out millions of pharmaceutical ads or phishing emails directly onto the internet using port 25.
So they were using regular people's laptops as spam cannons.
Exactly. To combat this, internet service providers made a drastic decision. They started blocking all port 25 traffic originating from residential home networks.
Just cut it off completely.
If you are on your home Wi-Fi, your ISP will not let you send data out on port 25. They reserve port 25 strictly for secure, verified server-to-server communication deep inside data centers.
Okay, but if my ISP blocks port 25, how does my laptop send a legitimate email to my Gmail server?
That is why port 587 was introduced. Port 587 is the designated port for client submission. It requires authentication.
Ah, so you have to prove who you are.
Yes. When your laptop wants to hand off a drafted email, it connects to your mail server on port 587, provides your username and password, proves you are a legitimate user, and then the server accepts the mail.
Okay, so SMTP on port 587 gets the draft from my laptop to my server. Then my server uses SMTP on port 25 to route it across the broader internet to the recipient's server.
He's got the relay race down.
But how does my server know where that recipient server is located? Like, if I email john@example.com, my server has to find the specific machine handling mail for that domain.
We are going right back to our city's phone book, DNS, but we aren't looking for a web server this time. We are querying a specific type of record called an MX record.
Mail exchanger records.
Yes. An MX record is a DNS entry that explicitly identifies which server is authorized to accept incoming email on behalf of a domain.
How does that look in practice?
So your SMTP server asks DNS who handles mail for example.com. DNS checks the MX records and replies, the mail server for that domain is located at IP address 198.51.10.14, and they have a backup server at 198.51.100.15.
It acts as a dispatcher for the mail truck. The coordination is beautiful. Okay, so the mail has traversed the internet and arrived at the recipient's server. It's sitting in a digital mailbox. But John, the recipient, still needs to read it on his phone.
And this is where we hit a fork in the road.
Right. The sources outline two completely different protocols for retrieving mail, POP3 and IMAP.
These are the mailbox access protocols. SMTP pushes mail outward, POP3 and IMAP pull mail inward to the user, and they have very different philosophies on how to handle that data. Let's examine POP3 first, the Post Office Protocol version 3.
POP3 uses port 110 for insecure, unencrypted connections and port 995 for secure SSL encrypted connections. What is the fundamental mechanism of POP3?
The defining characteristic of POP3 is a download and delete workflow.
Download and delete.
When your email client, say, Thunderbird on your desktop computer, connects to the mail server using POP3, it looks at the inbox, downloads every single new message directly onto your local hard drive, and then, crucially, it sends a command to the server to delete those messages from the cloud.
So the server is essentially just a temporary holding bin.
Exactly. It operates exactly like a physical post office box. The post office receives your letters and holds them in a metal box. You walk in, pull the letters out, take them to your house, and the metal box at the post office is now empty.
Because of this, POP3 is really designed for a single device ecosystem, isn't it?
Totally.
Right, because if I use POP3 to download all my emails to my desktop computer on Monday morning, and then I open up my smartphone on Monday afternoon to look for a specific receipt, the smartphone will check the server, and the server will be completely empty.
The email only exists on the desktop hard drive. It creates islands of data.
That sounds really frustrating for how we work today.
It is. Contrast that with IMP, the Internet Message Access Protocol. It operates on port 143 for insecure connections and port 993 for secure SSL connections.
Based on the pain of the POP3 example, I'm assuming IMAP is designed to keep everything everywhere all at once.
That is a great way to summarize it. IMAP's philosophy is synchronization. When you use IMAP, your device is not downloading and deleting. Your device is essentially holding up a mirror to the server. The master copy of the email lives permanently on the server in the cloud.
So when I open the Mail app on my phone, it just downloads a temporary copy to display to me.
Correct. And more importantly, its sync state changes. If you open an unread email on your phone, IMAP sends a message to the server saying, mark this message ID as read. An hour later, when you open your laptop, the laptop connects via IMAP, looks at the server state, and displays that same email as read.
And it allows for folder management too, right?
Yep.
If I create a folder called tax documents and drag an email into it on my web browser, that folder structure instantly replicates to my phone and tablet.
Yes. IMAP is the absolute standard for modern multi-device access. It allows you to transition seamlessly between a desktop client, a mobile app, and a webmail interface, always looking at the exact same synchronized inbox.
So here's a question that always comes up when comparing these two. IMP is so clearly superior for how we live and work today. Everyone has a phone, a tablet, and a laptop. The synchronization is mandatory. So why does POP3 still exist? Is it just a dusty relic from 1995 that we haven't bothered to turn off yet?
It's easy to assume that, but no, it is not a relic. POP3 is still heavily utilized in very specific, highly constrained enterprise environments, usually revolving around extreme privacy, security compliance, or severe infrastructure limitations.
Can you walk me through a scenario where a company would intentionally cripple their syncing capabilities to use POP3?
Let's talk about error gap security and data sovereignty. Imagine you're working at a defense contractor handling highly sensitive classified blueprints. You might have a strict legal requirement that sensitive communications cannot reside permanently on a third-party cloud server where they could potentially be compromised in a long-term data breach.
Because the data has to be controlled.
Right. With IMAP, that classified email sits on a server in a data center somewhere forever. With POP3, the company can configure an automated script to connect to the server every 10 seconds, download the encrypted emails directly to an isolated, highly secure local server deep inside their own building, and instantly scrub the external cloud server clean. They are using POP3 to minimize their attack surface.
That is a brilliant use case. It removes the liability from the public internet.
Another common use case is raw storage constraints. Imagine a small business that uses a cheap web hosting plan that only gives them 1 gigabyte of email storage space.
That fills up fast.
If they use IMAP, their inbox will fill up in a month, the server will reject new mail, and their business halts. If they use POP3 to constantly pull the mail down to their local massive multi-terabyte hard drives, they never hit the server limit.
So IMAP is for modern convenience and ubiquitous access, and POP3 is for ruthless local control and managing server footprints. And I should note, based on everything we discussed regarding HTTPS, regardless of which protocol you are using, you must always use the secure ports. Port 995 for POP3 and port 993 for IMP. Because using the old ports means sending your email password across the coffee shop Wi-Fi in plain text.
Absolutely. Secure by default is the only way to build a network today.
Okay, so we've got the mail trucks running smoothly. But email is really optimized for small messages, documents, maybe a few pictures. What happens when the city needs to move heavy cargo?
The big stuff.
Yeah, what if we're talking about transferring 50 gigabyte video files or organizing millions of complex municipal records? How does the network handle that scale of data?
This is where we move past simple web and email and start looking at file and print servers and massive database architectures.
Let's start with moving the heavy files themselves. The original workhorse here is FTP, the File Transfer Protocol.
FTP is a very old legacy protocol for transferring bulk files between a client and a server. It's an interesting piece of architecture because it actually uses 2 different ports simultaneously to manage the job.
Port 20 and port 21, according to the sources. How do they divide the labor?
Port 21 is the control port. It handles the administrative side of the conversation. This is where your client connects, sends your username, sends your password, and issues commands like list directory or delete file. And the other part. Port 20 is the data port. When you actually initiate a file transfer, the heavy lifting, the actual binary zeros and ones of the file, is streamed over port 20.
But the study materials are very explicit here, practically flashing warning lights. They emphasize that standard FTP is highly insecure.
It suffers from the exact same fatal flaw as HTTP and Telnet. It is entirely unencrypted.
Oh, it's another postcard.
A giant postcard. It was built for a trusting world. When you log into an FTP server, your username, your password, and the entire contents of the files you are transferring are sent over the network in plain text. It is a massive vulnerability.
So how do we move big files securely today?
We use encrypted iterations. The standard practice now is to use SFTP, which stands for SSH File Transfer Protocol.
How does that differ?
Instead of using ports 20 and 21, it wraps the entire file transfer inside a heavily encrypted secure shell tunnel on port 22. Alternatively, there is FTPS, which takes the old FTP structure but layers TLS encryption over it, similar to how HTTPS works. But plain FTP should essentially be banned on a modern network.
Good to know. Don't use plain FTP. But what about sharing files locally? FTP is usually used over the internet. What if I am sitting in an office building, I open my Windows computer, and I click on a shared network drive called Marketing Assets to pull up a spreadsheet? Or I hit print, and a document spits out of the copier down the hall.
For localized sharing, especially in environments dominated by Microsoft, the core mechanism is a protocol called SMB Server Message Block.
The sources show SMB operating over TCP port 445.
Correct. SMB is what allows Windows computers to seamlessly discover each other on a local network, browse shared folders, read and write files remotely, and send jobs to networked printers.
It seems like it's pretty deeply integrated into Windows.
Oh, deeply integrated. A modern optimized version of it is often referred to as CIFS, Common Internet File System, though the terms are often used interchangeably in the field.
Now, there is a historical protocol mentioned alongside SMB in the materials, NetBIOS, and its TCP/IP wrapper NetPT. The text describes it as an older method that allowed name resolution before DNS became the standard. Can you untangle that history for us?
It's a fascinating look at how networking evolved. Today, if a computer needs to find another computer, it queries a central DNS server. But in the 1980s and early 90s, when local office networks were just starting to be built, there were no local DNS servers.
The network was just a bunch of computers wired together in a single room.
Exactly. So if your computer, named Desktop 1, wanted to connect to Server A, how did it find it? Microsoft used NetBIOS. It was a broadcasting protocol.
Broadcasting like the DHCP megaphone we talked about earlier.
Very similar. Desktop 1 would essentially shout across the local wire, "Hey, who has the name Server A?" And the server would shout back its location.
That sounds like a localized, chaotic version of name discovery.
It worked well enough for small offices, but as networks grew to encompass thousands of computers across multiple floors, thousands of computers constantly shouting to find each other created massive broadcast storms that bogged down the network traffic. It was terribly inefficient.
So DNS stepped in to organize the chaos.
Yes, DNS provided a quiet, structured, central directory. Modern SMB over port 445 relies on DNS and IP routing. However, NetBIOS is a stubborn ghost of the past.
Is it still around?
It is often still enabled by default in Windows for backward compatibility with incredibly old software. An astute network administrator needs to know what it is, primarily so they know how to disable it to tighten security and reduce network noise.
Okay, so SMB handles our loose files, spreadsheets, Word docs, PDFs. But what if the data isn't a loose file? What if a company has a massive, intricate collection of interconnected records?
Like what?
Customer profiles, millions of financial transactions, real-time inventory tracking for a global supply chain. You can't just dump that into a shared folder. Our digital city needs highly organized archives. We need database servers.
Database architecture is a massive discipline of its own. A database server is a specialized machine entirely dedicated to ingesting, organizing, querying, and serving massive volumes of data at lightning speed.
And the materials highlight a critical architectural divide here. Relational databases versus non-relational databases.
This is a debate I hear constantly in the industry.
Let's break down the mechanisms, starting with relational databases. The text notes that these are still the most widely used type in the world, primarily utilizing SQL structured query language. How does a relational database actually organize information?
The key word is structure. Relational databases are incredibly rigid, strict, and predictable. They store data in structured tables composed of rows and columns. And the true power lies in how those tables link together, how they relate.
Let me try an analogy. It feels like a highly fortified, infinitely complex Excel spreadsheet.
That is the perfect starting point. Imagine you are building an e-commerce platform. In a relational SQL database, you would define strict rules. You create a customers table. The columns are customer ID, first name, last name, and email.
Okay, got the table.
The rule is, you cannot add a customer without an ID, and the email column must contain an @ symbol. It enforces data integrity.
Okay, so I have a spreadsheet of customers.
Then you create a completely separate table called orders. The columns here are ordered, purchase date, total price, and customer ID.
Because both tables contain a customer ID column, they share a relationship.
Exactly. That shared ID is the linchpin. If a manager wants to know, what is the email address of the person who placed order #500? The database uses SQL to perform a join.
How does a join work?
It looks at the orders table, finds order #500, sees that it was placed by customer ID #42, instantly jumps over to the customer's table, finds row #42, and extracts the email address.
It stitches the data together on the fly.
Yes. This architecture guarantees something called ACID compliance, meaning transactions are atomic, consistent, isolated, and durable.
What does that mean in practical terms?
If a bank transfers money from account A to account B, a relational database guarantees that if the deposit into account B fails for any reason, the withdrawal from account A is instantly rolled back. The data never ends up in a corrupted, half-finished state. It is perfect for banking, inventory, and anything requiring mathematical certainty.
That sounds flawless. So why did the industry ever need to invent non-relational databases? What is the flaw in the strict spreadsheet model?
The flaw is its rigidity. What happens when your data doesn't fit neatly into rows and columns? What if your data is chaotic, unstructured, or evolving so fast you don't have time to define strict rules?
Like trying to fit a square peg in a round hole.
Exactly. Every time you want to add a new column to a massive SQL table, you essentially have to lock the database and restructure millions of rows, which can take hours.
So if relational databases are rigid Excel spreadsheets, the analogy I like for non-relational databases is a giant reinforced bucket of assorted Legos. You sacrifice some of that strict mathematical consistency in favor of extreme flexibility, speed, and massive scale.
A bucket of Legos captures the essence beautifully. Non-relational databases, often called NoSQL databases, store data in completely different formats. Let's look at a document database, which is a very popular type of NoSQL.
How does that work?
Instead of a rigid row in a table, a customer's entire record is stored as a single, self-contained document, usually written in a format called JSON.
So all the data for one person is bundled together in one text file.
Exactly. Document 1 might contain a customer's name, their shipping address, a list of their last 5 orders, and an array of their dietary preferences.
Okay, that's one document.
Now here's where the Lego bucket comes in. Document 2, right next to it in the exact same database, might belong to a completely different type of customer. It might have a name, no shipping address, but a massive nested list of 50 different social media handles.
There's no master rulebook enforcing what columns must exist. The database just accepts whatever shape you throw into the bucket.
Exactly. You don't have to predefine the schema.
Yeah.
If your e-commerce catalog suddenly starts selling a product that requires 20 new attribute fields, you just start writing those fields into the new documents. The database doesn't care. It gives developers immense agility to iterate quickly without fighting the database architecture.
The sources also briefly mention graph databases under the non-relational umbrella. How do those work?
Graph databases are fascinating because they de-emphasize the data itself and focus almost entirely on the relationships between data points. Imagine mapping a social network.
Okay.
You have a node for John, a node for Sarah, and a node for a Nike shoe. The database stores the connections. John is friends with Sarah. Sarah purchased the Nike shoe. John liked a post about the Nike shoe.
It looks like a giant spider web.
Yes. If you try to query a SQL database to find all the friends of friends of friends who bought a shoe, it requires complex, computationally heavy table joins that can grind a server to a halt. A graph database traverses that spiderweb in milliseconds because the relationships are physically stored as data points. They are heavily used in recommendation engines and fraud detection.
So to summarize the archive rooms, if you were building a banking application where a single lost cent causes a legal crisis, you use a strict relational SQL database.
Definitely.
But if you are building a rapidly evolving mobile app, a massive IoT data ingestion engine, or a social network recommendation algorithm, you use the flexible Legos of a non-relational database.
Exactly right. Choose the right tool for the job.
So we have all these systems, SMB file servers holding confidential HR documents, relational databases holding millions of credit card numbers. How does the network ensure that only the right people get access to these vaults? You can't just let anyone who wanders into the digital city access the archives.
No, you definitely cannot.
You need a balancer and you need a VIP list.
Security access is one of the most complex logistical challenges in enterprise networking. Let's frame the problem. Imagine a medium-sized company with 500 employees, 50 different file servers, 20 databases, and a VPN for remote work.
Okay, that's a lot of infrastructure to manage.
If you manage security locally, you have to create a unique user account for every single employee on every single server.
So I have to manually type John's username and password into 50 different machines.
Yes. And what happens when John quits or gets fired on a Friday afternoon? The IT administrator has to race to log into 50 different servers and manually delete his account before he can steal data.
And if they miss even one server,
John still has a backdoor into the network. It is a logistical nightmare and a massive security vulnerability.
centralization is the only way to solve that. You need a single master ledger.
Exactly. And networks solve this using directory services. It is a single, centralized source of truth for every identity in the organization. And the protocol used to communicate with, query, and manage that central directory is LDAP, the Lightweight Directory Access Protocol.
The sources list LDAP operating on port 389 for unencrypted queries and port 636 for secure SSL connections.
Yes, and as always, port 636 is the standard practice now. The most famous implementation of LDAP in the world is Microsoft Active Directory. Active Directory is the brain of the corporate network, and it uses LDAP as its language.
So how does it change the workflow from the nightmare scenario?
When John tries to open a file on a random file server, that server doesn't maintain its own list of users. Instead, the server essentially pauses the request, reaches out over the network to the central Active Directory server using LDAP, and asks, I have a user named John trying to access this folder. Is he an active employee, and what security groups does he belong to?
The directory replies, yes, John is an employee and he's a member of the marketing group. The file server checks its own rules, sees that marketing has access, and opens the file.
And when John gets fired,
The administrator clicks one single button in Active Directory to disable his central account.
instantly, across the entire global network, every single server that queries LDP will be told that John's access is denied.
It is the ultimate VIP list. But simply being on the list isn't the entire security mechanism. The sources detail a foundational security architecture called the AAA framework. AAA. What does that acronym stand for?
AAA stands for Authentication, Authorization, and Accounting. It is the holy trinity of access control.
Let's break them down sequentially, starting with the first A, authentication.
Authentication answers the fundamental question, who are you and can you prove it?
It is the process of verifying a claimed identity. When you walk up to the bouncer at the club, you say, "I am John Smith." That is your identification.
But the bouncer doesn't just believe you. He demands to see your driver's license. In the digital world, providing your username is the identification. Proving it requires authentication factors.
Something you know, like a password. Something you have, like a physical smart card or a code sent to your phone. Or something you are, like a fingerprint or biometric facial scan.
Exactly. Multi-factor authentication combines those. Once you pass those checks, you have successfully authenticated. You are allowed past the front door of the building. But that brings us to the second A, authorization.
Authorization answers the question. Now that you are inside the building, what exactly are you allowed to touch?
Just because you proved you are a legitimate employee does not mean you have carte blanche access to the entire company. The receptionist who authenticates successfully shouldn't be authorized to open the CEO's payroll spreadsheet.
Right.
Authorization takes your verified identity, checks it against the access control policies, often pulling from LD-RU, and grants specific, granular permissions.
The bouncer let me into the club, but authorization determines whether my wristband gets me into the VIP room or just the main dance floor.
Precisely. And finally, we have the third A, accounting.
Which answers the question, what did you actually do while you were in there?
Accounting is the auditor. It quietly tracks usage, measures resources, and logs activity. It records the exact timestamp you logged in, the specific files you downloaded, the administrative commands you ran, and the time you logged out.
Why is accounting so critical?
2 reasons. First, security forensics. If a massive data leak occurs, you don't just want to know that an account was compromised. You need the accounting logs to prove exactly which files were stolen so you can notify the affected clients.
That makes sense. And the second reason?
Billing. If you are using a cloud service like Amazon Web Services, they use AAA accounting to track exactly how many CPU cycles and gigabytes of bandwidth you consumed so they can send you a bill at the end of the month.
So we have authentication, who are you, authorization,
Yeah.
what can you do? And accounting, what did you do? How does this framework physically play out when a device tries to connect? The sources map out a chain of command involving 3 specific components: the supplicant, the NS, and the AAA server. Walk me through this interaction.
It's a brilliant separation of duties. Let's use the example of an employee trying to connect their laptop to the corporate Wi-Fi network. The first piece of the puzzle is the supplicant.
That's a great vocabulary word. A supplicant is someone pleading for something.
Exactly. The supplicant is the device, or the software on the device, that is requesting access to the network. In this case, it is the employee's laptop. The laptop broadcasts its desire to connect, and it is intercepted by the second component, the NAS, or Network Access Server.
The gateway, the bouncer at the door.
Right. In our Wi-Fi example, the NAS is the physical wireless access point bolted to the ceiling. If you were dialing in remotely, the NAS would be the VPN server. The NAS controls the physical or logical port. It acts as a gatekeeper.
But the access point on the ceiling doesn't actually have the company's VIP list stored inside it, does it?
No, it doesn't. Its job is simply to hold the door shut and demand credentials. The supplicant hands its username and password to the NAS. The NAS packages those credentials up securely and forwards them deep into the corporate network to the third and final component, the AAA server.
And the sources list Radius and TACAS Plus as the primary examples of AAA servers.
Yes. Radius is very common for standard network access, while TACAS Plus is often used for authenticating network administrators who are trying to manage routers. The AAA server is the manager sitting in the secure back office. It holds the master keys.
So the AAA server receives the credentials from the NAS on the ceiling. It checks those credentials against the LDOP directory we talked about earlier. It performs the complex math of authentication. It checks the group policies for authorization.
And if everything checks out, the AAA server sends a secure message back to the NAS on the ceiling. Yes, this user is approved. Unlock the port, let their traffic onto the network, and apply these specific security filters to their session.
The NAS opens the door, and then I assume the NAS continuously streams accounting data back to the AAA server to log how long the user stays connected.
Exactly. It's a closed loop.
I want to pause and look at the macro design here. Why separate these roles? Why not just build a really smart Wi-Fi router that does the authentication, authorization, and accounting all by itself? Why involve 3 different devices?
Scalability and security. Imagine a university campus with 2,000 Wi-Fi access points spread across 50 buildings. If the access points were responsible for the VIP list, you would have to sync a database of 40,000 students to 2,000 separate devices every time someone enrolled or graduated.
Which is impossible to keep synchronized.
Right. And from a security perspective, those access points are physically accessible. A student could rip one off the ceiling in the library, plug a cable into it, and try to extract the password database from its memory.
That would be bad.
By separating the roles, the access points, the Nest devices, remain incredibly dumb. They hold 0 sensitive data. They are just empty gateways that blindly forward requests to the highly secured AAA server locked in a concrete bunker data center. It centralizes the intelligence while distributing the access.
That is a phenomenal piece of engineering. It keeps the edge of the network simple and the core of the network smart.
Exactly.
Okay, so our digital city is heavily fortified. The doors are locked, the bouncers are in place, the VIP lists are managed centrally. But how do the mayors of this city, the system administrators, actually manage this massive, sprawling metropolis? If they have 500 servers spread across 3 continents, they can't physically walk to every single building with a keyboard and monitor every time a setting needs to be tweaked.
No, that would be impossible. The scale of modern computing requires robust, secure, and ubiquitous remote access and monitoring services. This is the nervous system of city management.
Let's start with remote access. How do admins reach out and touch a machine that is 3,000 miles away? The sources list several protocols, starting with a comparison of SSH and Telnet.
Let's address the legacy protocol first. Telnet, operating on port 23, was one of the earliest remote access protocols. It allows an administrator to open a command line interface on their local computer, connect to a remote server or router, and type text-based commands as if they were sitting at the remote console.
But based on the pattern of these early protocols, let me guess, it's unencrypted.
Entirely. Telnet sends every keystroke, including the administrator's root passwords, across the network in plain text. If an attacker intercepts a Telnet session, they gain total control over the core infrastructure. It is a massive vulnerability and is almost universally banned on modern production networks.
So what replaced it?
SSH, which stands for Secure Shell, it operates on port 22. It performs the exact same function, remote command line access, but it establishes a heavily encrypted tunnel before a single keystroke is sent.
Using similar math to HTTPS, I assume?
It uses the same principles of asymmetric public and private key cryptography we discussed earlier to ensure that the session cannot be eavesdropped on or tampered with. SSH is the absolute gold standard for remote administration.
Now, I noticed an interesting historical footnote in the materials here. When discussing SSH and Telnet, it notes that this type of terminal access originates from early configuration by TTY devices, and that modern software like PuTTY or the Mac terminal just acts as a terminal emulator. What does TTY actually mean?
It is a beautiful piece of technological history that still defines how we interact with computers today. TTY stands for teletypewriter. If we go back to the 1960s and 70s, computers were massive mainframes that took up entire climate-controlled rooms. You didn't have a graphical monitor and a mouse.
How do you talk to it? Punch cards.
Before widespread monitors, you used a physical teletype machine. It was essentially a heavy electromechanical typewriter connected to the mainframe by a serial cable. When a programmer wanted to issue a command, they physically typed it on the typewriter keyboard.
And then what?
The machine sent electrical pulses to the mainframe. The mainframe processed the command and then sent electrical pulses back to the typewriter, physically hammering the text response onto a continuous roll of paper.
Wow. So the physical typewriter machine itself was the terminal. It was the end point of the communication.
Yes. The user interface was literally ink on paper. Now fast forward 50 years. When a modern systems administrator opens a little black window on their MacBook and types a text command using SSH.
They're using a terminal emulator.
Exactly. The software is virtually recreating the exact same text-based input and output paradigm of those old electromechanical typewriters. The underlying concept of sending a string of text characters to a processor and receiving a string of text characters back hasn't changed in half a century. We just digitized the paper roll onto a high-definition screen.
That is amazing context. Okay, so SSH is perfect for typing text commands into Linux servers or Cisco routers. But what if the administrator needs to manage a Windows server? What if they actually need to see a graphical desktop, click on the Start menu, and open graphical windows?
For that, you need a different protocol. RDP, the Remote Desktop Protocol. It operates on TCP port 3389. RDP provides full graphical user interface control over a network.
How does it manage that without massive lag? Streaming a 4K desktop video sounds heavy.
It is surprisingly efficient. RDP doesn't just stream a dumb video feed of the screen. It actually hooks into the remote Windows operating system's graphics engine. It sends instructions across the network, draw a blue square here, render this text font there.
Oh, that's clever.
It reconstructs the graphical interface locally on your laptop while sending your precise mouse clicks and keystrokes back to the server. To the administrator, it feels exactly like they are physically sitting in front of the remote machine.
And the final remote access tool listed is the VPN, the Virtual Private Network. Now, most people know VPNs as the app they buy to hide their IP address when downloading files or trying to watch Netflix from another country. But in an enterprise context, a VPN serves a very different structural purpose, right?
Vastly different. In a corporate environment, a VPN is about extending the physical boundaries of the digital city. Imagine an employee working from a hotel room in Tokyo, but they need to access a highly confidential internal HR server that is locked safely behind the corporate firewall in New York.
You can't just expose that HR server to the public internet.
Exactly. So the employee uses a VPN client on their laptop. It establishes a heavily encrypted, secure tunnel through the chaotic public internet directly into a VPN gateway sitting on the edge of the corporate network in New York.
Once that tunnel is established, how does the network view the laptop?
The network treats the laptop as if a massive invisible Ethernet cable was stretched from the hotel in Tokyo directly into a switch in the New York office. The laptop is assigned an internal corporate IP address. From that point on, the employee can use SSH, RDP, or SMB to access internal servers securely because conceptually they are inside the building.
So administrators have all these tools to reach out and fix systems. But how do they know when they need to intervene? You can't just randomly RDP into 500 servers every morning to ask them how they are feeling. How does the city management keep a proactive eye on the infrastructure?
This brings us to network monitoring, which is driven primarily by two protocols, SNMP and syslog. Let's tackle SNMP first, the Simple Network Management Protocol.
SNMP operates on UDP ports 161 and 162. How does it actively monitor the health of a network?
SNMP operates on a strict manager and agent architecture. Let's set the stage. The administrator runs a central SNMP management system, a dashboard software on their workstation. Meanwhile, on every single piece of infrastructure in the company, the routers, the switches, the servers, the battery backups, even the network printers there, is a tiny piece of software running in the background called an SNMP agent.
So the agents are spread out everywhere listening.
Yes. The primary mechanism of SNMP is polling. The central manager uses port 161 to constantly ping the agents on a schedule, asking for specific metrics. It asks the router, what is your current CPU utilization? It asks the switch, how much bandwidth is passing through port 5? It asks the server, how much free hard drive space is left?
The manager is constantly surveying the population.
Right, and the dashboard aggregates all this data into beautiful graphs so the administrator can spot trends, like a hard drive slowly filling up over a month, allowing them to fix it before it crashes.
The polling happens on a schedule.
Yeah.
What if the manager asks the router how it's doing at 10:01 a.m. and everything is fine? But at 10:01 a.m., a power supply blows up and the router catches fire. The manager won't ask again until 10:25 a.m. Does the admin just not know for 4 minutes?
That is exactly why SNMP utilizes port 162 for a mechanism called traps.
What is a trap?
A trap is a proactive, unsolicited alert sent by the agent. Instead of waiting to be asked, if the agent detects a sudden critical threshold violation, a power supply fails, a cooling fan stops spinning, or a network link drops, the agent immediately fires a high-priority trap message to the central manager on port 162.
It raises an immediate alarm.
Yes. The dashboard flashes red, the system sends an automated SMS text message to the administrator's phone, and they can react instantly to an outage.
Okay, so SNMP gives us the real-time health metrics, CPU usage, fan speeds, up-down status. What about syslog? The source is listed on UDP port 514.
If SNMP is the real-time health monitor, syslog is the historical paper trail we discussed earlier. Every piece of equipment generates text-based event logs. A firewall logs every denied connection. A server logs every successful and failed login. If you leave those logs sitting locally on 500 different machines, they are useless during a crisis.
Right, I'm not going to SSH into 500 different servers to read 500 different text files trying to track a hacker.
Syslog is the solution. It is a standard protocol that allows all those disparate devices to stream their log files over port 514 to one massive, centralized syslog server. That server aggregates, indexes, and makes all the logs searchable.
So it's all in one place.
If a breach happens, you log into the syslog server, search for a specific IP address, and instantly see a timeline of every single device that IP interacted with across the entire enterprise.
And to tie it back to our earlier conversation, this is precisely why NTP time synchronization is so critical. If the central syslog server receives logs from a router in a database, but their clocks are out of sync by 5 minutes, the centralized timeline is completely shattered. The logs become circumstantial evidence instead of proof.
Exactly. The systems are deeply fundamentally interconnected. You cannot have effective monitoring without synchronized time.
The final piece of city management highlighted in the materials is load balancing. What role does a load balancer play in the network?
Load balancing is about traffic management and survival. Imagine a company launches a highly anticipated new product, and suddenly a million people try to hit their website at the exact same moment.
A single web server, no matter how powerful, is going to get crushed by a million simultaneous TCP connections. The CPU will max out, the memory will overflow, and the server will crash.
Yes, so architecture demands horizontal scaling. Instead of one giant server, you build 10 identical web servers. But how do you ensure the traffic is distributed evenly among them? If you just list 10 IP addresses in DNS, users might all organically hit server number 1 anyway.
Enter the load balancer.
The load balancer sits at the very edge of the network, acting as a highly intelligent traffic cop. To the outside world, the load balancer is the website. It holds the single public IP address. When a million users connect, they are actually connecting to the load balancer.
And the load balancer decides where to send them internally.
Exactly. It uses algorithms like round robin, where it sends user 1 to server 1, user 2 to server 2, and so on. Or it can monitor the servers and say, server 4 has the least active connections right now, send the next batch of traffic there. It ensures no single machine is overwhelmed.
The sources also note that load balancing provides fault tolerance. How does that mechanism work?
The load balancer performs constant health checks on its pool of servers. Let's say server 7 experiences a catastrophic hardware failure and dies. The load balancer pings it, gets no response, and instantly removes server 7 from the active rotation. It automatically routes all incoming traffic to the remaining 9 healthy servers.
The end user sitting at home never sees an error message. They have no idea a server just exploded in a data center somewhere. The website just keeps loading.
It creates a highly resilient, self-healing infrastructure.
So, taking a step back, what does this entire suite of management tools mean for the IT administrator working a Friday night shift? It means that through SSH, VPN tunnels, SNMP traps, centralized syslogs, and load balancers, a modern infrastructure is designed to be highly resilient and globally manageable.
They can fix it from anywhere.
The admin gets an SNMP text alert on their phone that a web server is overheating. They see the load balancer is automatically taking it offline. They fire up a secure VPN tunnel from their couch, SSH into the overheating server, check the syslog to see what caused the CPU spike, and reboot the service, all without ever putting their shoes on.
It really is the pinnacle of remote orchestration.
But as we move into the final segment of our deep dive, we have to acknowledge a stark reality. Not every part of the digital city is a shiny new skyscraper running optimized load balancers.
Unfortunately not.
Every city has its historic districts with crumbling, unmapped infrastructure and shiny new suburbs built with cheap, unproven materials. Networks are no different. We are heading into the outskirts. Let's talk about the ghosts of the past and the Wild West, legacy systems and IoT.
Let's address the ghosts first. The materials define legacy, or end-of-service, EO systems, as hardware or software that is no longer supported by the original vendor.
Meaning the company that wrote the software, say Microsoft with Windows XP, or Cisco with a 15-year-old router has officially announced, we are done, we will no longer write security patches or updates for this product. It is abandoned.
Yes. Now, the logical IT perspective is if a system is unsupported and unpatchable, you turn it off and replace it. But the business reality is entirely different.
Why on earth would a multi-million-dollar corporation keep an end-of-service operating system running on their network?
Because migrating away from it is often unimaginably complex, prohibitively expensive, or sometimes physically impossible without destroying a critical business function. Let me give you a very common real-world scenario. Imagine a massive automotive manufacturing plant. They have a robotic assembly line that generates $10 million of revenue a day.
Okay, high stakes.
The robotic arms are controlled by a highly specialized, custom-written piece of software that was installed in 1999. That software was hard-coded to communicate using legacy protocols, and it only runs on Windows NT. The company that wrote the software went bankrupt 15 years ago.
Oh, I see the trap. You can't upgrade the computer to Windows 11 because the software won't run, and you can't buy new software because the company is dead.
Exactly. To replace that single unpatched Windows NT computer, the company would have to rip out the entire $10 million robotic assembly line and build a new one from scratch. The business executives look at that and say, no, keep the old computer running.
But the security risks must be catastrophic.
They are a ticking time bomb. If a new vulnerability is discovered in Windows NT today, Microsoft is not going to release a patch to block the attack. That system is permanently, irreversibly exposed. It becomes a soft, defenseless target for any malware that happens to find it.
So you have these fragile glass houses hidden deep inside the corporate network, and then on the complete opposite end of the spectrum, entering the network at an astonishing rate, we have IoT, the Internet of Things, the Wild West.
The materials define IoT as a network of everyday physical devices connected to the internet to share data. We aren't talking about laptops and servers anymore. We are talking about smart thermostats, internet-connected security cameras, smart light bulbs, medical infusion pumps in a hospital, or connected refrigerators.
And these are often embedded appliances sharing the exact same physical office space as the enterprise servers.
Yes. And this creates a nightmare scenario for modern network architecture. Think about the clash between these two extremes. You have a brand new, often incredibly cheaply manufactured IoT device, let's say a $15 smart light bulb bought off the internet for the break room.
I'm assuming a $15 light bulb does not have robust cybersecurity engineering behind it.
It rarely does. Many consumer-grade IoT devices have terrible default security. They have hard-coded administrator passwords that cannot be changed. They transmit data in plain text. They have tiny processors that cannot handle TLS encryption. And crucially, the manufacturer rarely releases firmware updates to patch vulnerabilities.
So you have this incredibly vulnerable, essentially unpatchable light bulb sitting on the corporate Wi-Fi.
And that cheap light bulb is on the exact same internal network as the ancient, unpatched end-of-service Windows NT database running the assembly line.
Oh, wow. I see how this connects. The attacker doesn't need to launch a sophisticated assault against the company's $1 million perimeter firewall.
No, they don't touch the firewall. The attacker scans the internet, finds the vulnerable smart light bulb or thermostat that is broadcasting out to a cheap cloud server. They easily compromise the thermostat. Now, the attacker has a foothold inside the building. From the thermostat, they quietly pivot laterally across the internal network, scanning for weak targets.
And they find the Windows NT machine, which has no defenses left.
Exactly. They use the shiny new toy to compromise the ancient ghost. By flooding our environments with IoT, we are vastly expanding our attack surface, creating millions of new doors into the network, while simultaneously holding on to unpatchable legacy vulnerabilities on the back end. Figuring out how to segment and balance the convenience of IoT with the massive security risks it introduces is arguably the hardest challenge in network engineering today.
That is a sobering thought. We have built an incredible machine, but it is incredibly fragile.
Very fragile.
Wow. Okay, we have covered a massive amount of ground today. Let's do a quick recap to tie all these mechanisms together. We started our journey in the digital city by looking at the foundations. We saw how DHCP acts as the welcome center, shouting over UDP to hand you a temporary street address and a map. We explored how DNS acts as the ultimate globally distributed phone book, instantly translating human names like example.com into routing IP addresses.
We explored the doors of the city, the ports. We learned the critical mechanical difference between broadcasting plain text over HTTP on port 80 and establishing a secure, mathematically locked vault using asymmetric cryptography with HTTPS on port 443. We ensured our digital clocks were perfectly synchronized down to the millisecond with NTP, calculating network transit delays so that security protocols like Kerberos don't lock us out for a suspected replay attack.
We visited the digital post office, watching SMTP act as the outbound mail truck, routing messages across the internet using MX records, while POP3 offered air-gapped local downloads and IMAP provided seamless multi-device synchronization. We moved heavy cargo with SMB and compared the rigid, highly structured spreadsheets of relational SQL databases to the infinitely flexible, schemaless Lego buckets of non-relational document and graph databases.
We met the bouncers of the AAA framework, seeing how a supplicant uses a dumb NAS gateway to authenticate against a centralized, intelligent LDAP directory, separating security roles for massive scale. And we watched the system administrators manage it all remotely using encrypted SSH tunnels, monitoring the real-time pulse of the city through SNMP traps and centralized syslog paper trails, while load balancers acted as traffic cops to keep the infrastructure resilient and self-healing.
And finally, we looked at the dark corners of the city, the compounding risks of blending unpatched, abandoned legacy EO systems with thousands of new, barely secured IoT devices. It is a brilliant, terrifying ecosystem.
It really is.
Which leaves us with a lingering thought for you to take away. We've built this incredibly complex, globally dependent digital metropolis on foundational protocols like basic TCP and UDP ports, SMTP and DNS. But remember the history we discussed. These protocols were largely designed decades ago, in an era of trusting university researchers long before anyone could imagine a hostile internet populated by billions of smartphones, nation-state hackers, and internet-connected refrigerators.
The foundation of the internet is fundamentally old, and we spend most of our time bolting new security layers onto it.
So as billions of new IoT devices flood the streets of our digital city every single year, generating unprecedented amounts of traffic and exposing massive new attack surfaces, will these old roads and traffic lights hold up under the pressure? Or are we rapidly approaching a day where patching protocols with TLS isn't enough and the entire architecture of the internet will need a fundamental ground-up rewrite?
That's the million-dollar question.
Something to ponder the next time you ask your smart speaker to turn on the living room lights. Thank you so much for joining us on this deep dive. Keep questioning the invisible infrastructure around you, and we will see you next time.